So hello everyone. First of all, I'm very happy to be here today, especially as it's my first conference of EuroLLVM. So thank you for the welcoming. It's very nice. I work at Kalray. I'm a compiler engineer, and we've been developing an LLVM backend for the Kalray VLIW core. So I will present you a bit of our experiences on doing so, with a focus on scheduling, because scheduling is a very important aspect in VLIW core's performance. So, in a nutshell, we are an emerging company of 100 employees, something like that, and we are developing a new processor with our own architecture. So we got a hardware team doing the designs, and we got the software team doing the compilers, the debugger, applications, libraries, operating system, you name it. So it's quite an impressive project. We are mostly based in France, but we also got antennas in the US and in Asia. So what we're developing is this architecture that is called the Coolidge architecture. So it's a manycore processor. It has 80 CPU cores that are divided into 5 compute clusters. And thanks to the network on chip, the clusters can send messages to each other through asynchronous write or read. So you can see on the middle side the compute cluster, what it looks like. It's got 16 cores, and it's got 4 megabytes of local memory. And then it's got a couple of units for writing to memory asynchronously, sending packets to the network, this kind of thing. And so this processor is supposed to be used either as an accelerator, so the host writes memory to the processor computes, and then the host reads the memory. Or it can also work as a standalone, so receiving data from the Ethernet and PCI. But as a compiler guy, I'm mostly interested in that part, which is the VLIW core, because that's what the LLVM is going to generate code for. So I'll start by presenting the VLIW core and its specificities from a compiler point of view. So what is interesting to know for the compiler. Then I detail a bit the scheduling part, how do we handle this, and how can we make it better. And then I do some performance comparison versus GCC. That will be more general than just scheduling. It's just a few examples that we stumbled upon. So this is the VLIW core that we are developing. So it's a 6-issue VLIW, very large instruction word processor. So it's an in-order pipeline, but you can execute up to 6 instructions per cycle. So that's what a VLIW is. So it's got 2 arithmetic logical units, 1 multiply accumulate unit for 14-point operations and multiplications, 1 load store, 1 branch control for branching, and we also got a coprocessor that we call the TCA. So the core processor has 64 registers of 64 bits, but the coprocessor has its own register bank of 48 registers of 256 bits and has specialized matrix multiplication instructions. But the tricky part is that in order to use this, you need to move the data with special instructions. So first you move the data, then you you write the instruction for the TCA, and then you write back the data into memory or into the core registers. So if I give you an example of the pipeline on our processor, so we got here I show you 5 stages. There's the instruction decode stage, the read register stage, and then we've got E1 to E3 for executing. In reality, it can go up to E6, but here I show you instructions that terminate at E3. So at cycle 0, I decode a bundle. So this is a load, and this is an addition. And these two are issued at the same cycle within the bundle. Then we go through the cycles. And then here you see that there's a read on R1. But since R1 is computed by the addition, and the addition only requires 1 cycle, this is OK for the pipeline. But if you go to the next cycle, you see that we require R0, But R0 is being computed by the load instruction, and the load on our architecture takes 3 cycles to execute. So the processor has to insert a stall. Our VLIW processor is what we call a VLIW with an interlock pipeline because of this, meaning that we don't have to insert knobs to ensure the correctness of the code. If we don't have the data yet, the core is just going to stall. And yeah, one small detail is that the whole bundle is stored. The instructions don't go away from the bundle. The whole bundle is stored and is going to wait. So this is an example of typical VLIW assembly code that we have on our architecture. So you see these double semicolons. These are the bundle separators. So they separate the instructions to be issued at the same cycle. And so the compiler job is to ensure that the bundles are as big as possible, because the bigger the bundle is, the more throughput we have. Ideally, so we are looking for a code with big bundles with hardware loops. You've got this hardware loop here, meaning that when I reach the end of the loop, it's going to branch for free without any penalty in branching. We're looking for a code with little to no stall, because if we have stalls, the performance goes down dramatically. And we want to profit of vectorized instructions, which is the case here. As you can see that we are loading 4 registers at the same time, so this is a 256 bits load. And here we are doing an addition on 4 integers of 16 bits at the same time. So that's what we want our compiler to generate in the ideal case. And so we support 2 compilers in our architecture. We've got GCC. So GCC, for now, is the most used compiler in our application because it's the oldest one that we have ported. We can compute the Linux kernel for architecture on GCC. And so we've got 2 main backend developers on GCC, and before there was Marc Poulies. And then we've got LLVM. So LLVM is the most recent addition to our compilers. What motivated the work of porting LLVM to Kalray was the OpenCL support. And we got 2 main developers, that are Diogo Sampaio and myself. So I'm the latest addition on the team. And previously there was Laurent Thévenoud with us. So now I'd like to take a focus on the scheduling on the VLIW core. So how do we schedule the VLIW core? Well, the bundles, they group instructions to be scheduled at the same time. And there's, well, as you might know, there's 2 main components for deciding the schedule times. There's the latencies and the reservation tables. Both are given by the architecture manual. So in our processor, if you have a piece of code, we are able to statically determine how many cycles it's going to take, assuming there's cache hits in memory. So some example of reservation tables. In the architecture manual, we know the total amount of resources that we have. So here, the issue resources, they count the syllables in the bundle. A bundle is maximum 8 syllables of 42 bits. So that's the 8 that you see here. Here I will show you the example where we have 4 tiny LU and 1 multiplier accumulate unit. So if I look at the reservation table of the multiplication of 2 registers, there's just 1 issue that has to be reserved because this is encoded in 42 bits. But if I want to add an immediate to the multiplication, then I'm going to require more issue resources because the instruction is going to be longer. So ideally, given this information of reservation tables and the information of the latencies, the scheduler should return for each instruction a cycle. And ideally, what we would like is that the bundling just packs the instructions at the same cycle together. For expressing this scheduling, we use like hexagon. So hexagon is another target that is, the hexagon target is upstream. and it's another VLIW processor. And we did like they did. We're using itineraries, and to model the fact that we are in a VLIW processor, we allocate all the resources at cycle 1, and then we release them immediately. So that's here. I mentioned that I had 4 tiny. So here this says at the first cycle, take 1 element of a tiny you see here. And then we've got the operand read and the operand write, so we were able to express that in the per operand model of the itineraries. So now about the scheduling optimization that I use in our backend. In LLVM, there's different scheduling passes. The first pass is the schedule DAG. This one is unavoidable. It's the pass that linearizes the selection DAG. You can have different heuristics, but for now we use the source scheduler. Then you got the machine scheduler in pre-pass. So pre-pass means before register allocation. This one can use either the itineraries or the write race. Write race is it's a newer scheduling model that you can write your backend with. Then there's the register allocation, and then we're using the post area scheduler for post pass, and we use the packetizer, the DFA packetizer here. So right now, the packetizer is the only solution that exists in LLVM for doing the bundling. And how it works is that it is greedy. As long as I can fit the resources in the bundle, the packetizer will put the instructions in the bundle. But what we have experienced in some of our benchmarks is that this may break the schedule because I was mentioning earlier that when there's a store, it's a whole bundle who stores. So if I have a greedy packetizer and I insert here an instruction ADHQ to a bundle that was not stalling, and if this instruction makes it stall, then I will lose 1 cycle in the end, which happens here, which is what happens here. Here you have the code after the scheduler, and this is the code after the packetizer. And instead of being at cycle 3 here I am at cycle 4 because this instruction made the whole bundle stall. So that's a bit of a shortcoming of the packetizer, and we've got some ongoing work to mesh the packetizer and the post area scheduler in one pass because the information to which cycle the instruction was scheduled has to be sent somehow to the packetizer. And the only way we found to do this is to merge them in one pass. So I did a bit of proof of concept with post area TD list, which was quite simple. I was inheriting from the post area TD list scheduler. And there's 3 methods. There's 3 methods of interest here. There's the enter region that enters a region to be scheduled. There's the schedule node top-down that says, OK, I want to schedule this node at this cycle. And then there's exit region where you exit and you free the data that you were using before. So I decorated this class to initialize data structures on enter region. On schedule node top-down, I store the cycle in some data class, and in exit region, I emit the bundles. But one problem that I found is that I cannot encode the issue resources because of some technical problems. The schedule post area TD list scheduler disregards completely the new micro ops variable. And this new micro ops, it's a variable that you can add to your instruction information in order to say, OK, this instruction uses that number of slots. And this would be a perfect fit for us for encoding the issue resources. But unfortunately, the scheduler does not support it, as it's older than machine scheduler. And also, I cannot add the issue to itineraries the way like I was doing with the other resources because the DFA packetizer generation explodes in terms of building time. The DFA packetizer is rather exhaustive. If you have too many resources that you have encoded, then you're going to, the LLVM did not compile anymore because of that. So I've got some work in progress to use the machine scheduler, but yeah, it's very early work in progress. So now I take a bit of performance comparison versus GCC to see. So we got two compilers, LLVM and GCC, and the benefit of having two different compilers on the same target is that we can compare them with each other, which is helpful to underline possible optimizations. So we did that on the polybench benchmark suite. Well, as a first disclaimer, the backend, our LLVM backend is less mature than GCC's, so we can still improve compared to GCC. But what we can see is that already for half of the benchmarks, LLVM is better than GCC. So that's very good. But we did find some performance culprits that you can see there. And I will outline a few of them. So one of the first culprits that we saw is that GCC, so given this piece of code here that sums the 9 adjacent elements of a 2D array, GCC is able to reassociate the operations. So instead of doing from left to right, it will do the 2 first, then it will add the third and the fourth, etc. And because of this, the GCC code has less stall than LLVM's because there's less data dependency that way. In LLVM, with that code, we stall every time. And since a 40-port instruction takes 4 cycles, well, you stall for 3 cycles every time. In this benchmark, I noticed a 36% performance difference because of these stalls. But what's funny is that I found an example where it was the opposite. GCC was reassociating, LLVM was not, and maybe because of luck, the LLVM code had less bundles than GCC, and so this resulted in a faster execution. The reason why is that GCC was multiplying AIK and AJK first, so the 2 elements need to be loaded before the multiplication, and this results in an additional bundle because you cannot load at the same time as you multiply the same element, but you're loading. On the other hand, LLVM was computing alpha times AIK, and so you could load AJK at the same time that you do the multiplication. So that's why there's only 4 bundles in LLVM and 5 bundles in GCC. This is an example that can be improved in all the backends because I saw that it was doing the same thing on x86 and ARM and but we also got examples, of course, where this is just our backend that is more tuning. For instance, here, on this piece of code, GCC was able to vectorize it by using 128 bits loads, and then this 40-point addition adds 2 40-point numbers of 64 bits at the same time. So per iteration, you're doing twice the number of computations than LLVM is doing. But we suspect that this is some tuning that we need to do in our backend. So that's just to say that we got some work to do on LLVM still, on our backend of LLVM. But another thing that we saw, and we were very surprised by this, is that the instruction combine of LLVM is very powerful. Here you've got a piece of C code. So it's doing saturated subtraction, and then it's doing an absolute value. And GCC was not able to recognize any of this. It did some generic if conversions that you can see with, this is a conditional move, and with a bunch of stuff to compute this. LLVM, on the other hand, was able to recognize that we got on our backend, on our architecture, we have a saturated subtraction, and we've got an absolute value. So we can just generate these interesting instead. And this results in a much better code. So that's it for me. I finished a bit earlier than I thought. Well, thank you for listening. So this is our GitHub, where we've got our own fork with the backend. And these are our mail if you want to send a mail to us. Yeah, so thank you.
Thank you, sir.
Oh yeah, and I forgot, if one of you is knowledgeable about software pipelining in LLVM, I would be very happy to talk with you. Thank you.
Questions?
Thank you for the talk. It's very interesting to see a talk on VLIW. I'm really interested in some of the performance data. You turned off aggressive.
Yeah.
Was there a reason for that other than to make GCC not look so good? Because it came across a bit like that.
Sorry?
So why did you turn them off?
Yeah, so that's because on Polybench, we were using small data sizes. And in the Polybench benchmark, the data initialization is done in the same computer unit, in the same compilation unit as the kernel. And what I was saying is that GCC was computing at compile time half of the values. So it was, I mean, to compare both compilers, it was a bit hard because of that. The constant propagation was much more aggressive on GCC than LLVM.
I mean, is that an improvement that's needed in LLVM?
Yeah, that's an improvement that could be needed. But I was focused here on the performance of the backend and in identifying what we can improve on at Kalray for. So that's why I turned this off.
Okay, that's reasonable. The second one was your GCC is quite a bit older than your LLVM because it's more mature. Yeah. Have you got any feeling for whether there's been, because there's been a lot of work on this, on GCC in the last 2 or 3 years. Have you got any feel for whether moving to a newer GCC would make much difference to what you're doing?
Sorry?
So you're using GCC 9. Okay?
Yeah.
GCC 12's just come out. Do you have a feeling for whether the improvements over that 3 years would make much difference to your performance? Yeah,
this is true. So we are working on upgrading GCC to GCC 10 and 11. It's a work in progress that we are doing right now. And yeah, it might very well affect performance even more, which is good news in a way for us because it means we will be able to probably outline more things that need improving. So.
Thank you for the talk. I'd like to know if you have any idea with the average size of the bundles and the average occurrences of stalls. If you build a big program like the Linux kernel, how much of your resources do you actually use and how much is left unused or stalled?
So the question is how much are our bundles always full? That's your...
Yeah, so do you have many empty slots in the bundles and do you lose many cycles to stalls after you schedule your code?
After you use what?
After you schedule the code.
After you use schedule? Sorry.
Yeah, so you have a bunch of resources, you have like up to 6 instructions per cycle. And the question is how much of it are you able to actually fill up with your optimizations and backend?
Sorry, I really can't understand the...
I can ask you later, no problem.
But maybe you can, I mean, yeah, there's the... well, our bundles are not always full because you, the code, it depends on the code. If you've got a lot of data dependencies, well, you won't be able to parallelize as much things. But there are optimizations like loop unrolling and register renaming that can make sure that you will have more register pressure, but then you will parallelize more. We haven't quite looked into that yet. Actually, there's an optimization called software pipelining that does that in a way, and we want to look into that after. But I don't know if it answers partially.
Yeah, it's a good answer. Thank you.
Okay, thank you.
One last quick question.
Not really a question, but we've been doing some work on software pipelining, so feel free to come talk to us after.
Thank you. Great. Awesome.
All right, we have time for one more quick question, if any. Right? Oh, how far to go to?
Thank you. In your first missed optimization example, you mentioned that the LLVM couldn't reassociate some operations. What was the reason? Was it because of alias analysis or any reasons?
Very good question. Actually, this is very recent finding because I did the polybench when preparing the slides, kind of. So it's very recent, and we want to look into that. What we know is that there are cases where LLVM is able to reassociate, but there are cases where it does not do it. That's how far. That's just how far we got for now. But yeah. We know LLVM is able to, Clang is able to reassociate the floating point operations, but here it did not do it. I don't know why yet.
Right, let's thank our speaker.
Thank you.